General relativity, step by step. I've defined the trace reverse perturbation h bar in terms of the original perturbation h in the hopes that using it will simplify the Einstein field equations, the linearized ones at least, which I've got written down here. So of course what I'm going to do is to substitute, I'm going to substitute for h bar, and I've got the equation written down here. Okay, well let's just have a look at it. Let's just go for it and see what happens. Well, the first line is di gamma, here it is, di mu of h upstairs mu sigma. So it's h from this formula here, bar mu sigma minus a half eta mu sigma times h bar plus, I've got enough space to write it there? Yeah, let's try plus there. This term here, di sigma upstairs, di mu downstairs, sigma di mu acting on, well, it's just the same thing but with mu gamma instead. So it's h bar mu gamma minus a half eta mu gamma h bar. Okay, that's two terms. Minus, it's not, yeah, there it is. Minus this term here, di mu, and that this is important. That's an important operator. We'll come back to that in a minute. Times h bar. What have we got? We've got a gamma sigma on the top. Gamma sigma minus a half eta gamma sigma h bar. Pinch in a little bit. Minus this term here, gamma sigma h. Di gamma di sigma h. Of course, that is a plus h bar. So we're starting to see how it's going to work. What's the next term I've got here? I've got a term here, which is a minus eta gamma sigma di beta di mu h bar beta mu minus a half eta beta mu h bar. That's that term there. Plus eta gamma sigma di mu downstairs, di mu upstairs times h. Oh, and that's a minus because it's h bar. Okay, what we're going to do with this? Well, I've noticed a couple of things that can simplify. Let's go to red. Using again the fact that the metric tensor eta is constant, and so it commutes past the differentials. So this term here is equal to this term here because, oh, it's a half. Oh no. That's a half, isn't it? Got di mu. Oh, I thought that would cancel out nicely, and it doesn't seem to be doing so. Okay, sorry about that glitch. I was just looking at this, trying to figure out what cancels with what. It's not entirely obvious. This term here is a plus 1, and it cancels out with that term there, which is minus a half, and that term there, which is minus a half. That's nice. This I'll use a different colour. This term here cancels out with that term there, and this term here. Yeah, this is a non-obvious term. What's happened is that that eta has brought this summing over mu has brought the beta. This term here is equal to, I'll write it out in black. This term here is minus eta gamma sigma, and then it's not di beta anymore, it's di beta downstairs, but it's not di mu, it's di beta upstairs times h bar. And because the beta is an umbral index, I can cancel it. It's the same thing as the mu here. So the blue lines all cancel out. We've got -1 plus a half plus another half. Whew, that's nice. I better write out what we've got so far because I'm gonna get it wrong. Let me zoom in a little bit. We've got di gamma di mu from up here, h bar mu sigma, plus di sigma di mu. All the trace terms have gone. H bar, oops, that's not gamma. Mu gamma, which is that term there, minus di mu upstairs, h bar gamma sigma, those terms have gone, minus eta gamma sigma di beta di mu, h bar beta mu, and the last term is this one, which is a minus eta gamma, no, it's a delta, sigma, oh no, the last term's gone. The last term's gone. 1, 2, 3, 4 terms. Okay, so it's a little bit simpler, and that equals the left-hand side, which was, in my formulation, 16 minus a 16 pi g stress energy tensor mu sigma. Okay, we're nearly there. I'm just going to look at the right-hand side for a minute. Just a sec. I'm just going to look at the right-hand side for a minute. I think I've made a sign error somewhere, but I'm just going to look at the right-hand side. So it's di mu h bar gamma sigma, which is this term here. No, I haven't. I'm going to leave that sign in. That's a minus. No, no, it isn't. I'm going to change the sign. Minus this one, di gamma di mu h bar mu sigma, which is that term there. Yeah. Okay, so I'm changing the sign. That's minus. That's a plus, so it went to a minus. That's a plus, so this one goes to a minus. Di sigma di mu h bar mu gamma, which is that term there, plus eta gamma sigma di beta, that's the final term, di mu h bar beta mu, h bar beta mu. Well, there we go. So there's 4 terms there. What I want to do is to observe that this one here is qualitatively different from the other ones, because this one, everything's summed over mu, but this one is summed across 2 operators. That's di mu, di mu. This one here is summed between an operator. The mu index is on an operator, and here it's on h. Here it's summed over the operator and h. Here it's summed over the operator and h. So this one is different. What I want to do is to transform these away because they're not helpful terms. But to do that, you need to use coordinate freedom. Coordinate freedom, which is the basis of the whole of general relativity. This is why relativity is so clever. However, coordinate freedom is a very, very powerful beast. It's a monster. It makes everything hard. It makes everything complicated. But without it, you haven't really got a theory. The whole point of relativity is that it works in any coordinate system you want to choose. And of course, what we want to do here is to choose a coordinate system that makes our equations simple. So if I can find a system in which h bar alpha beta comma beta, and now let me write it out in my usual notation, di beta h bar alpha beta equals 0. You see we're summing over the beta. There it is, and there it is. If I can find such a coordinate system, then that would be wonderful, because this term would vanish. Why would that vanish? It's because it's got that in it. This term would vanish because it's got that in it. And this term would vanish. The thing in the square brackets would all vanish if I could find a coordinate system in which this relationship here is true. It's reminiscent of the fact that the stress energy tensor T alpha beta comma beta equals 0, the covariant derivative of T is equal to 0, the divergence of it is equal to 0. It's the same mathematics, although the physics is different. So if I can find a coordinate system, I will be left with just this different thing here, which, as we'll see, is much easier to solve. So that's the problem we have. Can we find a coordinate system in which that thing there is true, in which this thing here is true? Well, yes, we can. Yes, we can. Of course we can. I wouldn't have been talking about it otherwise. And the thing we need to do is to investigate a thing called gauge freedom. Gauge freedom, which is a weakened form of coordinate freedom, which is appropriate for the linearized field equations, which enables us to insist upon this relationship here. And I'm going to do that over. It's not straightforward. It's going to be 5 or 6 screencasts, but I'm going to do it next in the next few screencasts, and I'll show you how to find such a coordinate system. Stop.